Welcome back to the deep dive. For years, we've talked about AI as, a tool,
Right.
a sophisticated search engine, maybe a text summarizer, a code generator that it sits there and waits politely for your next prompt. Today, we're putting that definition completely aside. We are talking about something fundamentally different.
Yeah.
We're talking about AI collaborators, autonomous agents that can act as true co-scientists.
That is the critical shift. These systems are moving past being digital assistants.
Far past it.
They're formulating hypotheses, they're designing experiments, and this is the crucial part, they're debugging their own thinking without constant human supervision.
Without someone holding their hand.
Exactly. Our sources today really provide the blueprint for this next generation, the AI co-scientist, and the sophisticated reasoning and the architectures that make this kind of reliable autonomy possible.
Especially in high-stakes fields like this, like scientific discovery.
Absolutely.
So our mission today is to unpack the how. How does an AI actually achieve this level of continuous planning and, self-correction? We're diving into these compound multi-agent systems designed to plan, execute, debug, and even make novel discoveries in a continuous loop. We are moving far, far beyond the prompt docs here.
And we have to. The scale of the problem really demands it.
Which brings us directly to our first section, the AI scientist accelerating discovery.
Right.
The foundational challenge you mentioned is that the biggest breakthroughs today, think of something like CRISPR.
A perfect example.
It requires integrating insights from all these diverse, often totally unfamiliar scientific fields. You're trying to connect molecular biology with computer science and genetics.
And the sheer volume of publications makes that transdisciplinary work
Well,
almost impossible for human teams alone. It's what we call a breadth and depth conundrum.
okay.
You can go incredibly deep in your one field, but the second you need to connect it to an adjacent, unfamiliar one, you just hit a wall.
And that's the gap the AI is meant to fill.
That's where the multi-agent AI co-scientist system, often built on a model like Gemini 2.0, really steps in. It's explicitly structured to mirror the entire scientific method.
So it's not one massive model trying to do everything at once.
No, not at all. It's more like a team of specialized AIs.
A team.
Exactly. You've got a component that's the literature searcher, another that's the synthesizer, another that's the hypothesis proposer.
And one to design the actual experiment, I assume.
And yet another for the protocol, yeah. And the key is that it doesn't just generate the first idea, think so.
And just run with it.
Yeah, right. Because skepticism is absolutely crucial to the scientific method.
So the system has its own built-in skepticism.
It implements its own version of rigor through these self-play strategies. It sets up an internal, simulated scientific debate among its agents.
A debate, so they argue with each other.
In a sense, yes, to challenge assumptions. It also uses a tournament-based evolution process to refine and rank all these hypotheses.
So it's survival of the fittest for ideas.
You got it. It might generate 50 ideas, pit them against each other, and only the absolute strongest survive to move on to the next phase.
That is incredibly robust. Okay, let's look at some examples of this in action. Nugget 1. This involves something called molecular validation. Expert researchers ask the AI to explain the existence of CFPICIs. I'm not going to try to say that full name again.
Yeah, that's awful. Capsid-forming phage-inducible chromosomal islands.
Right. Across bacterial species, what did the AI come up with?
It independently proposed the hypothesis that these CFPICIs interact with diverse phage tails to expand their host range.
Okay.
Now, here's the mind-blowing part that proves its efficacy. The human research team had already experimentally validated that exact hypothesis.
What?
But the results hadn't been published yet.
Wait. So the AI arrived at a complex, experimentally verified discovery entirely on its own, in silico, just by synthesizing public information.
That's the implication. It basically confirmed the human team's breakthrough before they even announced it. It wasn't assisting them during the experiment.
It was a parallel discoverer.
It's a parallel discoverer.
Wow. That is a massive validation. Let's pivot to Nugget 2, target discovery for drug development. The AI was tasked with finding novel targets for liver fibrosis.
A very complex disease. And this is all about speed and accuracy. Identifying targets is normally a long, high-failure process. The AI streamlined the whole hypothesis selection and found targets grounded in really solid preclinical evidence. And when they tested them,
It worked.
the targets showed significant antifibrotic activity in human hepatic organoids. These are sophisticated 3D cultures that mimic a human liver.
Right.
It just bypasses months, maybe years of typical pre-screening.
Okay, so if the AI co-scientist is great at these focus loops, how does the system manage a truly large, sustained research project?
That's where you need architectures designed for persistence, something like the Kosmos system.
Cosmos.
What's fascinating about Kosmos is that it solves the context drift problem. It uses what's called a structured world model.
Explain that for us. Is that just a fancy term for a huge memory buffer?
Not exactly. Think of it more like a persistent, evolving blueprint for the entire research project.
Okay.
It's managed by a high-level agent, and it structures all the context, the goals, the data, the failed attempts, and it orchestrates all the other parallel agents doing the work.
So it's a project manager and a memory bank all in one.
Precisely. And that sustained context allows Cosmos to run for 8 times as many iterations as other agent systems. It can carry out the equivalent of months of focused human research in a fraction of the time.
And we've seen this kind of data-driven approach lead to physical discoveries. The most famous one is probably the antibiotic Epicin.
Oh, the Epicin story is a fantastic demonstration of this.
Mm.
Researchers used a specific type of model, a directed message-passing neural network.
Right.
And they trained it on growth inhibition data from about 7,500 molecules. The goal wasn't just to find any antibiotic, but one for Acinetobacter baumannii.
Which is a really nasty one. It's one of those superbugs, right? Highly resistant.
Exactly, a very challenging gram-negative pathogen. And the model, it made its predictions, and that led directly to the discovery of abelacin, a structurally new compound that was highly effective.
It just shows you can compress that pipeline from years of screening down to rapid, intelligent prediction.
That's the promise.
So this transition from prediction to physical validation is huge. But if discovery relies on this continuous internal planning, the next question has to be, how do these systems manage that plan?
Right. Now we need to get into the engine room, how these systems actually, well, how they think.
That sets us up perfectly for section 2, the architecture of reasoning.
Yeah.
You said something earlier that really stood out to me. You said that chain of thought, or code, is being seen as a crutch.
Well,
That feels like a huge statement. I mean, code is what made LLMs seem like they could reason in the first place.
it is a huge statement, but it really speaks to the limitations of trying to scale it. Kosmos forces the model to externalize all of its reasoning into token-level language.
That has to talk itself through the problem.
It's literally narrating its thinking out loud. And that's slow, it generates a ton of tokens, and if one little linguistic step is wrong,
The whole chain collapses. It's brittle.
very brittle. So if narrating your thinking is slow and brittle, the next frontier has to be moving that computation internally.
And that's latent reasoning.
Exactly. Latent reasoning is about doing the heavy lifting inside the model's hidden state space. Think
Yep.
about the human brain. When you're concentrating, you don't translate every microstep of your thought into language.
No, of course not.
You sustain these long, coherent chains of thought silently. Latent reasoning is aiming for that same kind of efficiency.
It's the difference between doing calculus on a whiteboard versus just knowing the answer.
Kind of. But that requires incredible computational depth, which is notoriously hard to achieve in these models.
Vanishing gradients and all that.
That's the engineering challenge. And that leads us to the Hierarchical Reasoning Model, or HRM. You can think of it as building a specialized brain within a brain. It's designed to massively increase the model's effective computational depth without just stacking millions of layers.
So how does that brain within a brain actually work?
It uses 2 coupled recurrent modules.
Yeah.
You have a high-level, or H, module for abstract, deliberate, slow reasoning,
The strategist.
the strategist, and then a low-level L module for the fast, detailed computations, the tactical steps. It lets the system manage thought on multiple timescales at once.
That high-level strategic process, it sounds a lot like what we've heard about tree of thoughts, or TOT.
They absolutely work together. Tree of thoughts is the deliberate strategy the AI uses. It maintains a tree of potential next moves.
Right, these intermediate language sequences.
And it actively self-evaluates its progress. It combines that language generation with classic search algorithms like breadth-first search for systematic exploration.
So TOT is the search strategy, and an architecture like HRM is the optimized internal engine that can actually sustain that deep search.
That's a perfect way to put it. It's the infrastructure supporting the strategy.
And we should probably acknowledge the foundation for all of this.
Of course. Underpinning all of it is the transformer architecture.
Attention is all you need. What's the key thing for you to remember about the transformer in this context?
It's the ability to model long-range dependencies. Before the transformer, models really struggled to connect the beginning of a long text with the end.
They lose the plot.
They'd lose the plot. The self-attention mechanism lets the model weigh the importance of every word against every other word. That creates the coherent, long-form understanding that is absolutely essential for the kind of complex planning an AI co-scientist needs to do.
That's the engine.
It's the foundational engine enabling all of this advanced steering.
Okay, but if these systems are so good at thinking and planning, our whole conversation hinges on one thing: trust. And LLMs have a massive, well-known flaw we have to talk about.
The hallucination reality.
Yes.
It is the single biggest hurdle to high-stakes applications. Our sources are unambiguous on this. Hallucinations are an inherent, unavoidable property of these models.
Because it's just predicting the next plausible token, not the next true fact.
Exactly. And critically, they struggle with intrinsic self-verification. They don't know what they know, so they'll fabricate facts with complete confidence.
Which means relying on the model to grade its own homework is a non-starter. This is why self-correction frameworks that use external tools are becoming mandatory.
Right.
Let's start with CRITIC, correcting with tool interactive critiquing.
CRITIC is designed specifically to break that internal confirmation bias. Its main contribution is integrating reliable external tools to enforce an iterative cycle.
That cycle will be
Verify, then correct, then verify again.
Ah.
It pulls the model out of its own head.
Can you give us a concrete example of that tool integration?
Sure. For a QA task, if the model generates an answer, CRITIC might use Google Search as an external tool to check if it's true. Or, for content moderation, it might use the Perspective API to get a fine-grained toxicity score. The key is that the tool provides an objective, measurable standard.
And it actually works. It's not just added overhead.
Oh, it yields significant improvements. CRITIC dramatically improved performance across the tasks they tested. It confirms that tool interaction is necessary for reliable self-improvement. Reliability is now an architectural feature.
Not just a hope. Okay, that makes sense. Now let's talk about a different type of self-improvement: learning from mistakes. This brings us to reflection.
Reflection is fascinating because it's so lightweight. You don't have to fine-tune the whole massive LLM.
So what does it do?
When a plan fails, a separate self-reflection model analyzes the failed trajectory.
So it's like the model writes a journal entry about what went wrong.
That is a perfect analogy. It produces a summary of verbal feedback, like explicit instructions for the future. And that feedback is stored as episodic memory to guide its next attempt.
So it uses language, the very thing that makes it probabilistic, to create these non-probabilistic, high-value memories of failure.
It is highly effective. In trials, Reflection improved performance on decision-making tasks, like in AlphaWorld, by 22%.
22% is a huge jump.
A huge jump. And it improved reasoning tasks, like Hotpot QA, by 20% over strong baselines. It's leveraging that explicit memory of failure to form a better plan.
Okay, finally, let's look at the highest stakes scenario. Specialized domains like medical research, where factual accuracy is absolutely non-negotiable.
Right. Knowledge graphs.
Exactly. When you're dealing with precise, structured information, LLMs often just insert fabricated facts. How are systems dealing with verification there?
They need specialized, almost brute force verification. Systems like GraphMERT focus on distilling only explicit, verifiable factual triples. They aren't trying to generate new facts.
They're trying to extract only what can be proven.
A critical difference. They're moving from generative AI to a highly restrictive, verifiable extraction.
And
By being so rigorous, GraphMERT got a validity score of 68.8%, so nearly 70% of its facts were accurate, compared to only 43% for LLMs. And get this, they use GPT-5 as a tool in this process, but only to validate the consistency of the extracted data.
So we're seeing this clear hierarchy emerge. The AI agents for high-stakes tasks are built not just with generative power, but with these built-in external verifiers.
Which can include other advanced LLMs. The self-correction loop has become multi-layered and mandatory.
This has been such a deep dive into the guts of AI autonomy. To summarize the core transition we've seen, AI systems are fundamentally shifting. They're going from passive answer generators to active managers of context, optimizing their own thinking, and performing really sophisticated external verification.
The combination of latent reasoning, multi-agent management like Kosmos, and mandatory self-correction like CRITIC, it's all leading to systems capable of genuine, reliable autonomy.
And the takeaway for the bigger picture?
It's clear. The future involves a powerful, high-throughput, human-machine team of scientists and AI agents.
A partnership.
A true partnership. And for that to succeed, the ability for these autonomous systems to be transparently monitored, controlled, and to have their nuanced decisions explained, It is absolutely essential, especially as we start exploring uncharted territory at machine speeds.
That need for clarity and control is paramount, but that leaves us with a final thought for you to take away. If these self-adaptive autonomous systems can continuously optimize their own internal reasoning, apply sophisticated critiques, and drive new molecular discoveries faster than any human team, what then becomes the most critical, uniquely human role in the scientific process?
Something for you to ponder as these agents continue their work.